right, week 6.2, because I made half of these notes last week. We're going to be going over section 3.4, 3.5 like it says. Then we're going to have a little bit of a review section, just to kind of touch back on some of the stuff we've done up to this point. Having said that, let's get into everything. 3.4. So let's imagine we're manufacturing a box, right? Or we're filling a box. What we want is for this box to have a surface area of 108 square inches. How can we maximize the volume of this? What do y'all think? How are we going to set up this problem? Well, first, let's just start by tracing all of this out, getting an idea of what everything looks like. Belongs in the Louvre, right? That's what that museum is in France, right? The Louvre, or is it the Louvre? I don't know. I'm not an art student. Anyhow, all right, so we've got this box. Its base is going to be x by x. And its height is going to be h. Now we're told the surface area of this box is going to be 108 inches squared. So let's draw out what that might look like. So we know the base is going to be x by x, so it's going to have a surface area of x squared, right? And if we're going to fold all this up, then these little winglets, they're going to be x by h. So they're going to have an area of xh. We have 4 of them. So we know that the surface area is going to be equal to x squared plus 4xh, and this comes out to be 108 inches squared. Everybody agree with this? So the volume of this box is going to be x squared times h, right? Because think of it like taking the surface area of the base and extruding that up through the height. Make sense? So we get the volume too. The volume is x squared h. Now we want to maximize this. How are we going to do that? Well, to maximize the volume, we're going to have to find some way of getting a derivative out of this, right? So we got this h term, and we've got an x term. So which derivative are we going to take? I say let's take x, but first let's solve for h up here and then plug that in. Make sense? So doing that, this first equation is going to tell us that we can solve for x, yeah? The way we can do that is we can say, all right, let's separate x and h from each other as best as we can. So first, let's subtract x squared from both sides. This is going to be equal to 4xh. Now we can divide both sides by 4x. So h is going to be equal to 108 minus x squared, all divided by 4x. Is this divisible by 4? Yeah, it is. It should be what? 7? Yeah. All right. So because this is divisible by 4, we can reduce this to 27 over x minus x squared, or my mistake, x over 4. Is everybody with me on this? Now, we're going to take this and plug it into that. Is everybody cool with this? When we do that, we're going to get x squared times 27 over x minus x over 4. Well, hey, this x and this x is going to cancel, right? Like we can have some reductions in here. We're going to have 27 times x, because like I said, these x's cancel. So we're going to lower that by a power and just still multiply by 27. And over here, we're going to increase this by a power of 2. So we're going to have 27x minus x cubed over 4. Yeah? So let's make some more room for ourselves by erasing some of this.
Why would it be x cubed and not x squared?
Because we had x squared times x over 4.
Okay, sorry.
Make sense?
Yeah.
Cool. All right, so now we have volume written as an equation of just x, right? And we can differentiate with respect to x here. So the derivative of volume with respect to x is going to come out to be 27 minus 3 over 4 x squared, right? And we're going to set that equal to 0. we solve for x, well, x squared, this is going to give us 27 is equal to 3 over 4 x squared multiplying both sides by 4 over 3. We're now going to get 108 divided by 3 is equal to x squared. Yep. 108 divisible by 3, yes, because all of our digits add up to math trick. If a number, given a number, if all the digits add up to something divisible by 3, that number is also divisible by 3. So we know this is going to be divisible by 3. In particular, it's going to come out to be 36. So then we have x must be equal to plus or minus 6, right? Because we just took the square root of both sides. So we have x now. Because we know x has to be positive in this case since it's a physical system, and what's a negative length, right? So we know from this that x has to be 6 and I erased our equation for h, but h should have been 27x minus x over 4. So now to solve for h, we just plug in x equal to 6. Is everybody cool with this? So just really quickly comparing what we've done to what they've done. Started off by drawing the box, right? And labeling what all the dimensions were. And by pointing out that the surface area was going to be 108 and equal to x squared plus 4xh. Then going through and solving all of this, I said, all right, volume is going to be equal to x squared h. The surface area is going to be x squared plus 4xh. So h can be solved for here, right? That way we can plug it into our original equation. When we do that, we get 27x minus 1 over 4 times x to the third. And finally, solving everything, we find that x has to be equal to 6. Does everybody follow this idea, what we've done here? Like, why did we use the derivative here and set it equal to 0? Why did that happen? What do y'all think? People at home, why do y'all think I took the derivative and set it equal to 0?
To find the critical values.
Yes. Why is that? What does the critical value tell us? It tells us possible maxes and mins, right? And if we consider our system here, we weren't going to have a min. We had to have a max, right? Because what we could do is send x really close to 0 or send h really close to 0. But somewhere in between, we knew that the volume was going to have to be big. Does this make sense? Does everybody follow that logic? Kind of, sort of. I'm assuming from the silence that a yes. But having said all of this, let's move on.
I had a quick question.
Yes, ma'am.
For h, how come it was just x over 4 and not x cubed over 4?
I might have written something wrong here. No. Okay. So for h is actually 108 minus x squared over 4x. So we can break this up into two different fractions. And I have a typo on the board. Yeah, I wrote this wrong on the board. This h here was supposed to be 27 over x. So that was my mistake writing it just now. Does that answer your question?
Yeah, that helps. Thank you.
Awesome. Yeah, sorry about that. All right, moving on though. The general process of solving these optimization problems, the first thing I would suggest, and generally is just a good guideline, is to sketch out your problem if you can. Draw it like what we've done up here. Then identify what it is you're trying to minimize or maximize. In our case, that was the volume. They call it your primary problem or your primary equation here. Then you're usually going to be, not usually, you're going to be given another equation that's going to let you bound things, to solve for things. In our case, that was the surface area. Notice the surface area had to be bounded, right? It had to be 108. And that allowed us to solve for h. From there, we were able to set up a system of derivatives, find their critical values, and use that to maximize our system. Now notice, we could have chosen any other value here for surface area. Say 244, or 144, or 36, whatever we'd like. We'd come out with different x values, but the reason why this works is because this relates h to x in a way that constrains what x can be. Does that make sense what I mean? Folks at home, do y'all follow that logic?
Yes.
Yeah, awesome. And then from there, like I said, we just apply calculus. Once we get this primary, secondary equation done, or identified rather, and then solve for whatever values we need to solve for, then we can just go ahead and apply calc. All All right, so I think I'm gonna let you all try this one on your own really quick. We've got the product of two positive numbers is 288. You want to minimize the sum of the second number and twice the first number. For those of y'all at home, this is slide 7 on week 6.2. I'll give y'all like 5 minutes, give or take, to do this problem. So, looking at this problem, who was able to solve it all the way? Were any of you all able to? No? Got 12? Awesome. So, the way this problem works, so first thing we want to do is we want to identify what this is even got set up. What's going on in this problem, right? So we're told two positive numbers, they multiply to be 288. So we've got an x and we've got a y. Because we want to identify them as being different from each other, right? We're going to multiply them together, we're going to get 288. That's our primary equation. I mean our secondary equation in this case. The reason why it's our secondary equation, because what we want to minimize, what we want to optimize in this case, is the sum of the second number and twice the first number. Now, here I chose to set y equal to the second number, x equal to the first number. So we have y plus 2x is equal to the sum. And x times y is equal to the product, which we know comes out to be 288. Now this is the thing we want to optimize, right? This is our primary equation here. That means x times y has to be our secondary equation. The problem also tells us that the numbers have to be positive. So that means we know they're 0 or larger, right? Make sense? Okay. So if they're 0 or larger, we should just go ahead and note on that. Just put it off to the side because this is going to be useful later on. Now, using the secondary equation, we can set up a system to solve for y, right? But if you look at this, before we said x could be 0, now x can't be 0. Which makes sense because the product's going to come out to be 288. Okay, so we've got y is equal to 288 divided by x. Why don't we plug that in to our original equation, our original primary equation, right? That's how we got to the sum here. Now, with that in mind, let's take the derivative, because we're going to need to optimize this, right? So let's take the derivative, and let's set it equal to 0. Setting it equal to 0 gives us that 2 minus 288 divided by x squared is equal to 0. From here, we can solve for x, right? Just following all the math here. And we get that x is equal to plus or minus 12. Well, going back to our initial setup, we know that x has to be greater than 0. So we can choose, or we can eliminate rather, the negative value automatically. So all of this is to say, what we've got down here is that x has to be equal to 12. Since x is equal to 12, then we have an equation relating x and y. Let me write this in yellow down here. Since we have this equation relating x and y now, we can go ahead and solve for y as well. 288 divided by 12 should come out to be 24, I think. So comparing our solution to theirs, Theirs is a little bit more involved. They identified their primary equation and their secondary equation. They used their secondary equation to set up a relationship between x and y. And then they plugged it into their primary equation. This told them that x had to be greater than 0. Then they applied the derivative and solved for x. Notice we get two critical numbers. That's what they're saying here. But we're only concerning ourselves with one of them. So they went ahead and did a little bit extra. They actually checked to make sure that this is going to be minimized and or optimized, right? However you want to say it. So in this case, since s is decreasing on the interval 0 to 12 and increasing 12 to infinity, we must be at a minimum point, right? When x is equal to 12. So as a result, we know that we found the minimum. All right. Considering another example, we want to find the points along the graph closest to the point 0, 2. Let's look at what this looks like. What we're trying to do is say, all right, we're given this graph 4 minus x squared. We're given a point 0, 2. Now what we want to find are the points on the graph that are closest to the point 0, 2. And to do this, we're going to need to use a little bit of Pythagorean theorem. Or rather, the distance formula. So let's look at it and work on this problem. Oh, really bad. All right, so we've got this graph. This is the point -2, 0. This is the point 2, 0. That means this is the point 0, 4. We've got the point 0, 2 halfway down this. All right. The first thing we need to remember is that the distance between this point and any point along this graph, so this distance is going to be the square root of x minus 0, that quantity squared, plus y minus 2, that quantity squared, right? So we're going to take the square root of x minus 0 squared plus y minus 2, that quantity squared, check it out, every y value along this graph is going to have to be equal to x minus, 4 minus x squared. Agreed? So that means the point here is actually x and 4 minus x squared. So we can plug that into this. And when we do, we're going to get that d is equal to x squared plus 4 minus x squared, that's our y, minus 2, that quantity squared. Let me clean this up so that it's a little bit easier to read. X squared plus 4 minus x squared minus 2, that quantity squared, all of this to the 1/2 power. All right, so all I've done here is I plugged in 4 minus x squared for our y value, right? Notice when we do that, we can go ahead and cancel, get rid of this negative 2 and this 4, right? And reduce this just a little bit to being x squared plus 2 minus x squared, that quantity squared, all taken to the 1/2 power. Everybody agree with this? Now, question. If we want to minimize this, do we have to actually consider everything, or can we just like work a part of this? What I'm trying to ask is, can we just pull out what's underneath the radical and work on that instead? Should be able to, right? Because we know, excuse me, we're trying to minimize the distance, right? And if we're trying to minimize the distance, then whatever underneath here can't be negative because the distance has to be a real number, right? So let me explain, or show rather, what I'm trying to say. All right. They went ahead and simplified all of this as much as they could. Now, when we go through to evaluate what the critical points are of this, we can make the observation that D is smallest when the radical under the expression is smallest. Or I mean, the expression under the radical is the smallest. So, in other words, this distance is going to be its smallest value whenever x to the 4th minus 3x squared plus 4 is the smallest. As a result, we can get rid of that radical and just worry with finding what this is at its smallest. Everybody cool with that? So what we should come up with is y is equal to 4. think. No, never mind, I take that back. Okay, so from here, for the sake of time, since all we have to worry about is what's underneath the radical, taking the derivative of that, we're going to get 4x cubed minus 6x. Set that equal to 0. Factor out 2x from both sides. This thing is now only going to be equal to 0 whenever x is equal to 0, or when x is equal to the square root of 3 over 2, or negative square root of 3 over 2. So we have 3 critical points we have to consider now. And when we go through and actually apply our first derivative test, we're going to find that x equal to 0 is a relative max, meaning the square root of 3 over 2 and the negative square root of 3 over 2 must be relative mids. Is everybody cool with this? Is this making sense to everyone? Folks at home, are we making sense of all of this?
Yeah.
Yeah, awesome. In that case, what time is it? 16. All right, we're going to go through one more problem really quick. All right, in this other problem, we're going to try and minimize the amount of paper needed, given that we're only going to be allowed to print on 24 square inches of this paper. And we need the margins, top to bottom, to be 1.5 inches, and left to right to be 1 inch. So what does this look like? Let's jump to the next slide. This looks like this. We've got this piece of paper. We're only printing in this small area. This is going to have a surface area of 24 inches. Now, we know the length left to right is going to be the length of this plus our 1 inch margin on either side. And we know top to bottom, our length is going to be the length of this plus 1.5 inches on either side of our margins, right? So the entire piece of paper is going to have an area of x plus 1.5 plus 1.5, so x plus 3, times y plus 2, right? So this lets us set up the problem now. Our primary equation is going to be the equation of the area of the entire sheet of paper. Our secondary equation is going to be the equation for the printable area. From our secondary equation, we can set up a relationship between x and y. Plug that into our primary equation. And then apply the derivative. So when we plug that relationship between x and y to our primary equation, we're going to simplify to this point. Take the derivative of this. Set our derivative equal to 0. and solve for x. Then we're going to say, hey, the negative values aren't sensical because, again, what's a negative length? So we're going to choose only the positive values, plug that into our equation for y. We're going to get the length accordingly. Make sense? Having said that, I will let y'all go. I'll stick around if y'all have any questions.